So today we're doing two sets of notes. We have 6-5e notes that we're starting out with. It's all about graphing rational functions. Do you remember what the shape of the graph looks like for a rational function? Oh yeah, there we go. Hyperbola, yes. Yes, the finger placement is, yes, accurate. Hyperbola. So 6-5e notes, those are going to go on page 82 whenever we're finished. I asked you to have your notebook out and starting at 6-5a because all the things that we've done in the 6-5 blank notes are going to show up here. So you know how sometimes we do a lot of things and they don't seem too tough, but then all of a sudden we put them all together and then you freak out. Today is one of those freak out days, but I don't want you to do any of that because I want you to be prepared, which is why I asked you to have your notebooks, okay? You are going to have to take some initiative today. You're going to have to find things in your notebook and use them on these notes, okay? It's not hard to do, but we are putting a lot of stuff together. So in order to graph hyperbolas, so the shape of a rational function, we've got to do several things. The first thing that we need to do, and it's the first thing that we do in like all Unit 6 stuff, is to do what? Factor. So you factor all the parts. Break it all up because you're going to need all the parts. You ready to do some notebook research? Well, it says find the blank using the original denominator before simplifying. So I want you to go look in your notes right now, and I want you to figure out what fills in this blank that you use the original denominator for. So go fill it in on your own. I'm going to pause the video. Find the blank using the original denominator before simplifying. Raise your hand if you can tell me what set of notes this is from. Yes, ma'am. The orange ones?
It's the orange one, right?
I don't know. 6 dash what? It's not in that one.
6-3b.
Nope. Remember I told you to start from 6-5a. That's where you start from. That's what you start from. And you're thinking like find the LCD using the original denominator. That's not what I'm doing with this. I'm finding something that relates to a piece of the hyperbola. So starting at 6-5a, what do you use the denominator for? To find the what?
The whole or the asymptote?
6-5a.
The only x values that are not possible in a rational function are the ones that make the denominator equal to 0. So to find the domain of the rational function, set the denominator not equal to 0. So here, I need to find the domain using the original denominator before simplifying. So I find the domain. And then after I find the domain and I have already factored, if a factor cancels out, then a what occurs? A whole, good. If a factor cancels out, then a whole occurs. And that's 6-5b notes. If you're trying to figure out where the whole exists, you set the canceled factor equal to 0. You solve and get your x value. And anytime you have an x value in an equation, you can substitute x back in and you can get the y value for it. So the whole is an ordered pair. So after that, we're going to use the reduced form. So once you take the whole out, if there is one, use the reduced form of the function to find the blank asymptotes. Vertical, and then find the horizontal asymptote if one exists, because remember there's a possibility that there is no horizontal asymptote. And there are also slant asymptotes that may occur, but that's the 6-5f notes that we're going to do after this, so there will be no slant asymptote on our problem today. Would you like me to repeat that? Yeah, there could be a slant asymptote, but in this problem that we're doing in this set of notes, there will not be one. Because the next set of notes we do today, the 6-5F that you also picked up, that's the one where we talk about what a slant asymptote is and what it looks like. So no slant asymptote on this set of notes. Next, I need to find the blank intercept. So set the simplified function equal to 0 and solve for x. What kind of intercept do I solve for x on? Interesting. If you solve for x, that means you get an x value. So this is the X intercept. What do you replace x with 0 for and solve for y? The Y-intercept. And then finally, you need to take all of this information and you need to graph the function using the information from above. So using the asymptotes, using the places where there might be a hole, the intercepts, and then it's possible that you will have to make a table for some additional points because there might be a part of the graph that you don't really know what's happening. So if you create a table and pick some x values, you can substitute them and you can find the y values for them. So I'm going to go ahead and move this down. There we go. I'd like it to be straight. There we go. Good enough. That's fine. Okay, so in the example, it says identify the key features and graph the rational function. I'm not going to keep flipping between the top steps and the bottom, but you need to constantly be looking at the top. So in order to start the process of graphing, step 1 is to do what to all the parts? You need to factor all the parts. So I'm going to let you do that. I'm going to pause the video, and we're going to talk about the factored parts. All right, so in the bottom polynomial wasn't really tough to factor, right? Magic numbers, one is positive and one is negative though, so make sure that you have them in the right spot. I accidentally wrote x plus 1 for the second one, and it should have been x minus 1, so do as I say, not as I do. I make the mistakes. But on the top one, the magic numbers, I need to be two numbers that multiply to give me -6 and add to give me +5. So what two numbers do that? 6 and 1, which one needs to be negative? 6 and -1, yes. So out to the side, I'm going to make my 4-term polynomial 6x minus 1x. And I need to factor by grouping. So what GCF can be taken out of the first pair? 2x. What's left over when I take out a 2x? X plus 3. And the second group almost looks like x plus 3, but the signs are wrong. So what am I going to take out? -1. So -1 comes out and x plus 3 stays. So my factors are x plus 3 and what? 2x, yeah, minus 1, because that's kind of the leftovers. So there's my factored function, but what do you notice? What was that? There's a hole, right? Where x what? Where x plus 3 is equal to 0. So if I cancel those out, then I'm going to end up with what on the top? 2x minus 1. And what on the bottom? X minus 1. Yeah, because the x plus 3s are the things that are canceling out. Good. So I factored. I have my simplified version. I need to go back through and start finding the important pieces that are going to allow me to shape the hyperbola for my rational function. So for the domain, go back up to the top. It says find the domain using the what? Original denominator. So if I go look at my notes from 6-5A, to use my original denominator, I need to set the denominator what? Not equal to 0. So my domain will be all real values, except x is not going to equal some stuff. So here's my two pieces of the denominator. If I set these not equal to 0, that means that here x cannot be what? -3. And here x cannot be what? +1. So there's my domain. All real values, all real numbers, except x cannot be -3 and x cannot be 1. The wholes. Step 3 says if a factor cancels out, a whole occurs. So what do I need to do with the factor that we cancel out? Set it equal to 0. So x plus 3 equals 0, x equals -3. That's the x component for the ordered pair. But I need the actual location for the whole. So I need to do what with -3? I need to substitute, I need to put it in. And so if I'm trying to calculate that y value, I'm going to take 2 times -3, -6, that's right, minus 1, -7, that's right. So that's my numerator. And then the denominator is what minus 1? -3 minus 1, which you're right is -4. So what happens when you have -7 over -4? Turns into +7 over 4. Which you are going to have to graph this. So I asked my second period class, I said, well, do you know kind of where this falls on a number line? And the answer was silence. So in order to figure out where this kind of falls on a number line, you would try to do long division and figure out what the remainder is. So what is 7 divided by 4? How many times does 4 go into 7? 1 time. 1 times 4 is 4. If you subtract, you get 3. So 3 is the what? Remainder. So it's 1 and 3 out of what? So 1 and 3/4 seems like it's a little bit easier to place on a graph because you kind of know how far between 1 and 2 it is. So just an idea for you moving forward, if you get an improper fraction, this is kind of how you figure out where that point is on the graph. So I found the domain, we found the wholes. We want to go find the vertical asymptotes, which starts kind of that second chunk of steps in your notes. It says find the vertical asymptotes, but how do you do that? Set the denominator equal to 0. Didn't we already set the denominator? Let's see. Here's my notes on the asymptote, 6-5C. So to find the vertical asymptote, set the denominator equal to 0, factor if possible, and solve for x. So didn't we already set the denominator not equal to 0? Yeah. Didn't we already get some values? We got -3 and 1, correct? But why was -3 an x value that we couldn't have? What's at x equals -3? There's a hole, right? So there's not an asymptote, but there's a hole. That means that the vertical asymptote occurs where x equals what? No, not at -3. There's a hole at -3. The other number is the 1. So there's a vertical asymptote at x equals 1. And officially, I get that by taking the denominator, x minus 1, and setting it equal to 0. So x equals 1 is the vertical asymptote. Okay. This is what we did on our notes for 6-5C. Okay. The horizontal asymptote, there are some choices, right? You either have a no horizontal asymptote, or a horizontal asymptote of y equals 0, or you have y equals some other kind of value. So I'm going to pause the video. I'm going to give you a chance to refresh your memory on the 6-5C notes, especially the horizontal asymptote section, and then we're going to talk about this problem. Okay, so for the horizontal asymptote, you were supposed to look at the 6-5C notes, and so, oh wait, is it 5C? Yes. So if the degree of the denominator is greater, then that means y equals 0 is the horizontal asymptote. Do we have that situation here? No. Is the degree of the denominator greater? No. They're equal degrees, right? So we have a degree of 1 and a degree of 1. So my horizontal asymptote is y equals the ratio of the what? The ratio of the coefficients. Good. So what's the coefficient of the x term on top? 2. And this coefficient is 1, so it's 2. Yeah. 2 over 1 is just 2. Yeah, so the question that came up was, I thought that it was the degrees. Well, the degrees tell you if the degrees are the same, they tell you to take the ratio of the coefficients. So these being the same tell you to look at these numbers, okay? We're not taking the ratio of the degrees themselves. That's a good point to clarify. So let's talk about the range. For a hyperbola, you know what that looks like. You know that the arrows extend to the left and to the right. You also know arrows extend from the bottom to the top, right? So the range should be all real numbers, with the exception of y values that are either not there because there are holes, or y values that are not there in the range because there's a horizontal asymptote. And I believe we have two situations that will affect the range. We have a hole and we have a horizontal asymptote, correct? So the range is all real numbers except y cannot be equal to what? Tell me about the hole. What can y not equal? -3 is the x value. I don't care about that. Y can't equal 7/4 because there's a hole where the y value is 7/4. Y can also not equal what? 2 because there's a horizontal asymptote where y equals 2. So those are my two values for the range that cannot occur. Okay. Next up is the X Intercept, which is an ordered pair with 0 for its what value? 0 for its y value. So from yesterday, our notes asked us, in order to find the X-intercept, to take the function and set it equal to what? Set it equal to 0. And when we did that, because this is a rational function, what were we really setting equal to 0? We were really setting the numerator equal to 0. And what is the numerator in this problem now? 2x minus 1. So I'm going to take 2x minus 1. I'm going to set it equal to 0. I'm going to solve by moving the constant. So plus 1. 2x is equal to 1. And then, yes, if I divide by 2 on both sides, you get 1/2. And I know I'm running out of space. So 1/2. Let me move this down a little bit. Here we go. Okay. Tell me about the Y-intercept. Y-intercept is an what? What is this called? It's an ordered pair with the 0 and the x, yes. And how did we find this yesterday? Plug in the zeros in all the x places, yes. So instead of 2x minus 1, I'm going to have 2 times 0 minus 1. What is 2 times 0 minus 1? -1. So that's my numerator. And then in the denominator, instead of x minus 1, I have 0 minus 1, which is -1, which is really just 1. So I've got all the pieces, and I have a lot of pieces. You need to graph the asymptotes, you need to graph the holes, the intercepts, and then if you need some extra values, you can create a table. So let's go ahead and graph the asymptotes first, because those are the easiest things to put, and they kind of give your graph boundaries. Okay? So vertical asymptote, vertical, straight up and down, occurs at x equals what? X equals 1. So I'm going to go find x equals 1, and I'm going to put a vertical asymptote right there. I'm using a dashed line because it's not part of my hyperbola, but it's kind of a boundary for my hyperbola. It's like repelling my hyperbola, like a magnet. Like a what? Ah, yes. Okay. What about the horizontal asymptote? Where does that occur? Y equals 2. So horizontally, where y equals 2, there's an asymptote there. So 1, 2. Draw my horizontal line. Okay. So there's the two asymptotes. Remember that a hyperbola kind of looks like this and then like this. So there's two separate parts that we're going to be drawing, and the asymptotes kind of separate those parts. So in addition to those asymptotes, we need to put the hole in there. The hole occurs at -3 comma what? -3 comma what? 7/4, which we found out was kind of like graphing 1 3/4, 1 3/4. So I'm going to go plot the hole, but when I put it, I'm not going to put a closed point. I'm going to put a what? An open point. So the hole occurs at -1 2 3 comma 1 3/4. There's kind of an open hole right there. And I need to graph the intercepts. So the Y-intercept looks pretty easy to graph. 0, 1. 0, 1 right here. Then the X-intercept is what? Where's the X-intercept? 1/2, 0. Yeah, how do I graph 1/2, 0? Where do I go from the origin? Not up, because it needs to be on the x-axis, because it's an X-intercept. To the right, how much? Just a half of a box, right? Does this look like it could create part of the hyperbola? Yeah, it sure does. In fact, it looks so good that I can go ahead and trace what this part of the hyperbola looks like, making sure that I don't trace the hyperbola through the hole. I need to stop where the hole is, pick up my pencil, and then finish on the other side. Or my pen, sorry. Remember that hyperbolas approach the asymptotes, but by the very nature of an asymptote, the graph will approach it and never touch it. So it will get closer and closer, but it will never touch. So even if it looks like it touches, you need to understand that it doesn't. Try very hard to make it not touch. So I have this part, but I'm missing what I know should go up here, correct? So what was the very last step when we're graphing? If you're missing a part of the graph, how can you figure it out? Maybe. I don't know. What does the last step say? Look at step 8. Graph the function using information from above. Then what? Make a table for additional points as needed. So I need to make a table. You don't have to put a bunch of values in it. Maybe just 1 or 2. But I need x values for this. So what x value should I probably try and find a point for? Well, 1 is an asymptote, so there's no point there. But 2 would be good. To figure out how much I need to go up, that'd be good. And then maybe the next x value, so maybe 3. Okay, 2 and 3. All right, so if I'm trying to find the x values, and I have the function, the simplified function was 2x minus 1 over x minus 1. If I have that function and the x values, how can I get the corresponding y values? If I have 0 for x, how did I get the y? Plug in 0 for x, right? If I have 2 for x, how do I get the y? Plug it in for y, yeah. So what is 2 times 2 minus 1? 3, yeah. 2 times 2 is 4, minus 1 is 3. Over, what is 2 minus 1? So 3 over 1 is really just, there's a nice point. So I'm going to go plot the ordered pair 2, 3. Over 1, 2, up 1, 2, 3. So far, your guess of it needing to be symmetrical kind of looks nice, right? So we've got this point that's like over 1, down 1, and this point that's over 1, up 1. It's looking good. Now I need to go calculate the y value when x is 3. So what do I need to do with 3? Plug it in. Yeah, so 2 times 3 is 6, minus 1 is 5, and 3 minus 1 is 2. So 5 over 2 is my y value. 5 over 2 is really 2.5. Good. So I'm going to go over 3. 1, 2, 3. And I'm going to go up 2.5. 1, 2.5. And now I have an idea of how my function is supposed to be. So I'm going to finish graphing the hyperbola. Kind of a sketch. Looks good, right? Okay. So in general, we've taken all the things from 6-5 notes, A, B, C, and D, and we put them all together to do 6-5E, which is graphing, right? We found domain and range, we found holes, we found asymptotes, we found the intercepts, which is what we did yesterday, and it all comes together to make the graph. What's the hardest part about this set of notes? Too much work. A lot to remember, yes. So it's not so much that the math is hard. Like I can totally set x plus 3 equal to 0 and I can solve, or I can like substitute a value in and I can figure out the y value that goes with whatever x value I had. But it's remembering all of the things, which means that whenever you take a test over this, you're going to have memorized how to find the domain, how to find the asymptotes, how to realize when the horizontal asymptote is 0 or it doesn't exist or it's some other number. You might want to make some flashcards and not have like values on them, but have like how to find the domain and then set denominator not equal to 0, and how to find the holes, set canceled factors equal to 0 and solve. Like you might want to make flashcards that talk about the concepts. That way you can remember them. Okay? So I'm going to switch over to the 6-5F notes. They're similar, but what are they titled? Slant asymptotes, yes. Slant asymptotes. Let's see. There we go. Okay. So the slant asymptote notes are going to go on the next page. So that's page 83. And we're not going to finish them today. We'll finish them in class tomorrow, so that'll be okay. But they are going to go on page 83. The idea is the same as the previous set of notes. All the steps are the same. The way that you do everything is the same. So we're going to go through and we're going to identify the key features of this new graph that's given to us, and it is going to have a what? Slant asymptote, which means it is not going to have a what? Very good. Not going to have a horizontal asymptote. So let me move this down. Here is the function. As in all Unit 6 things, I need to start out by doing what to my function? Factoring. So I'm going to pause the video, and you need to factor the function. All right. So listen to my question. Not what you think the question is, but listen to my question. My question is, what are the magic numbers for the numerator? 1 and 1. Good. So what are the factors for the numerator? X plus 1 and x plus 1, which could also be written as x plus 1 in parentheses squared, right? So x plus 1 quantity squared. What's the denominator? X. So to find the domain, I want to take the denominator and do what with it? Set it not equal to 0, right? Because when the denominator equals 0, that part is not in my domain. So my domain is all real numbers except x cannot equal what? 0. Because the denominator is x, right? So x cannot equal 0. Holes occur when the function has what? Factors that what? Cancel out. Do we have that here? No. So are there any holes? No. Say that again. Well, it doesn't matter. Ask. That doesn't necessarily mean there's no horizontal asymptote, but there isn't going to be one because there is going to be a slant asymptote. Okay. Vertical asymptote comes whenever you do what? The numerator or the denominator? The denominator. So if I set the denominator equal to 0, the denominator is x, and x equals 0. And we already talked about how there's no horizontal asymptote just because in the notes today we're doing a slant asymptote for this problem. That's what it's titled. But how would I know that there's no horizontal asymptote just by looking at the problem? The exponent on the top is just in general bigger than the bottom, right? So that means that there's no horizontal asymptote. But if the exponent on top is bigger than the exponent on bottom just by 1, that means that there is a slant asymptote. So 2 is bigger than 1, and it has a difference of just 1. So I'm going to have to figure out the slant asymptote. And I'm replacing the screen with my notes from 6-5C that say, to find the slant asymptote of a rational function, use long division, or if you don't need to do long division, then you don't have to as long as you can just divide. So do I need to do long division here? No, because it's not a binomial. So I can just take each of the terms of the numerator and divide them by what? X. So I'm going to do that out to the side. I have x squared divided by x plus 2x divided by x plus 1 divided by x. Right? This is what happens when you divide by a monomial. Dividing by a monomial is example 1 in your 6-2A notes. So if you need a refresher, you can go back and look at that. So x squared divided by x is x, and plus 2x divided by x, 2, and then plus my remainder of 1 over x. And remember, we talked about, for the slant asymptote, we really don't care much about the remainder, we care about this. So my slant asymptote happens where y equals x plus 2. Happens where y equals x plus 2. You don't write the remainder. No, ma'am. Okay. The range. All real numbers. It's got to start out with that because it is a hyperbola, so it's going to go from negative infinity to positive infinity. But we need to see if there are any holes or any horizontal asymptotes that might remove some y values. So do we have any holes? No. Horizontal asymptotes? No. So anything keeping the range from being all real numbers? No. So the range is all real numbers. X intercept means you need to set the function equal to what? 0, which means you really are setting the numerator equal to 0. For each factor, if you set it equal to 0, it gives you the same little equation. X is equal to -1. Good. And then for the y-intercept, that is where x is 0. But wait a second. You do, yeah, you want to plug in 0 for x. But if you plug in 0 for x, 0 plus 1 is 1. 1 times 1 is 1. But then you divide by 0. Yeah, oh shoot. We can't have that because there's a vertical asymptote where x equals 0. So that means, is there any y-intercept? No, because there's a vertical asymptote on the y-axis. None. None. And we're not. Because this is the end of what we're doing today, and tomorrow we're going to put all of this together, and we're going to find the graph of our hyperbola.